Hey everybody, this is Larry. This is me going over Q4 of the bi-weekly contest 48, maximize score after n operation. So this is one problem where you look at the constraints first, or maybe second after you look at this problem. But after you look at this, for me, when I look at this problem, I go, okay, I think this is really hard to do because you have a lot of decisions and you have to figure out. So then the first question I may ask is, can I brute force this, right? Or can I, in a way, dynamic programming or memorization it, right? And because of that, the first thing I do will be look at the constraints. And my sort of constraint is you go to 7 or 14. I don't know why they, I know why they phrase it like that, but it's still like a little confusing. I have to double check that my math is fast enough. But yeah, then I know I'm going to do some sort of brute force. So yeah, hit the like button, hit the subscribe button, join me on Discord, let me know what you think about this problem, and note that you could watch me solve it live during contests afterwards, so you could see, like, I know what I don't like is how people sometimes like frame it like, oh, I knew the answer from the get-go, and like explain the problem as if they knew everything. So you can watch me solve it live afterwards during the contest where there's no fakeness, right? It is me, the scores up there and stuff like that. But yeah, but basically the idea is just, and this is will take a lot of practice. It's dynamic programming, it's memorization. It's called bit mask dynamic programming is a common name for it. But I think using bit mask is just a confusing term, or not a confusing term, but if you're a beginner, that term, bit mask dynamic programming, is very intimidating, I know, and I'm going to try to explain that a little bit, and why it is, hopefully extends it to other problems, ideally. But yeah, but bitwise dynamic programming, it's really just about, so a bitwise function, right? What are bitwise functions? So basically, for small n's, so let's say for n is less than 20, maybe even a little bit smaller, depending on, because sometimes Python is a little bit slower. But basically the brute force, what you want to do is called something called power set. A power set is basically the set of all the sets inside the set. If you want, for example, a power set, let's say you have this input. A power set may just be 1, 2, 1, 2, 1 and 2, 1, 3, 1 and 3, 2 and 3, ... I mean, I'm not going to count all of them, and it also has like stuff like 1, 2, 3, and so forth, right? So yeah, so that's a power set, and there are ways to represent this. For example, because that n is equal to 6 elements, right? In this case, then that means that you can have a Boolean array. So you have a Boolean array of, in this case, true, meaning whether this number is in the current power set. So this is true, true, false, 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 false. And then, I'm just going to shorten it with ft, f, and then tt, f. I'm just mapping these, right? Because one is in there, so it's true. 2 is in here, or actually going the other way around. If you look at this one is in the current set, so it's true. 2 is in the current set, so it's true. 3 is in this set, so this is just going to be ff, t, f, and so forth, right? And all the way up to 1, 2, 3 would be TTT, FFFF, or FFF, something like that, right? So basically, that's the idea about representing. Okay, you have n elements. You want the power set, which is trying all combinations. If you think about it, because yeah, that's just literally trying every combination. Because if you think about how many what numbers are left, that's the way you can think about it. Okay, so then now you went from here to converting it to a true false table, and then now we just have to convert that. Let's say in this case you have now let's say that you have this. Well, now you just have to convert that into a binary number. right? So you can think about that as 1 0 0 0 0 0 1 0 0 0 0. I might, and so forth, right? I think there's an extra F in here, but whoops. Dot 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 1 1 1 dot dot dot, right? And there's more, of course. So then now, so now these are just numbers, right? And they're bit masks, and that's basically that's the entire thing about bit masks. Bit masks are just a Boolean array that is compressed into one number for space efficiency purposes. And so you don't have to be intimidated by it. And then there's a couple of operations that you can do. Usually you'll see something like one left shift of I. That is just to get, if I is equal to 0, you have something like this. If I is equal to 1, you have something like this, and so forth, right? So basically, this is just to, shift the bits around. And then you have the AND operation just to check whether there exists. So then now, for example, you have a, let's say you have, let's just say you have some other random bit mask. And then you AND this by 1 shift I, which is for where I is equal to, say, 2. This allows you to check the second bit because that's just, checking whether that checks whether this is a 1, right? And if you have AND, that's basically the idea. You have the OR operation, which is also the same idea, except for it flips it. So if you have, this, where I is equal to, say, 0, then, you have these, and then when you flip the OR operation, you get, this, right? Oh, oops. Right, so that's the AND operation, and this is the OR operation. And basically from that, I'm not going to go for every one of these. I think that actually there's just an XOR. XOR is the other one. So maybe I will go with where XOR, let's just say 2, right? Because you have you have XOR, it equals 2, what? Exclusive OR, right? So then what ends up happening is AND checks for whether there's a 1 in that digit, or checks to see, or flips a digit from 0 to 1, and XOR, for me anyway, flips that digit. And you can combine them in different ways for different logic. Depending on context, I do different things, and there are more operations than this. But basically, the idea is that these are just, you have a set represented as a bit mask, or a number of bits, and these are set operations. I have a full tutorial on bit mask. You could maybe check it below. I hope this is a good introduction to it, because I don't usually go over this, but hopefully this is a good video for that. Yeah, and yeah, once you have that, then it becomes easier, because the idea behind using a bit mask is that literally you're trying every possible combination, right? Because here you can use the numbers at most once, and at 0 or 1 time, so that you can represent the number of times we use each number 0 or 1 time, which is also coincidentally the binary numbers. So in that way, it's just brute force. And now setting everything up, let's go. So basically, this is my recursive dynamic programming function, and it's basically saying, okay, given I, and I is defined in the problem. So yeah, and mask, which contains a binary binary table, or basically contains a set of whether X is available to be used, say, right? Yeah, let's say you have these masks. Return the best results. I mean, that's basic as defined as the problem as well, and that's just in the formula. And for me, a 1 in the mask means it is available to be used. Yeah. And so now you can think about it as if mask is equal to 0, all bits were used. And then this is just an n squared brute force, in that, you know, we check, you know, x can be used? Yes. And y can y be used? Yes. If that's the case, we calculate the score of this current thing. I mean, this is just a pre-calculation just in case. I wasn't sure if it's going to be fast enough. You can do it. I don't know if you could do it without it. In other languages, you probably could do it without it, but in Python, it's been a little bit slow, so I've been doing this lately. But yeah. So this is just the score defined in the function. And then now, we used x and y, and we go to the next index. That's basically what this is, right? Use the, you know, the score is calculated as defined in the function or in the problem. You know, use up mask or use up x and y, and then go to the next index, right? And this is just brute forcing every one, because you take the best one out of using x and y. Because if score is greater than best, then you just, you know, you set the best as your score, and then you return at the very end. And then of course we use the memorization on it. This is a standard thing people do in competitive. Not going to go over that particular piece in a bit, but just know that it gets memorized depending on the input. For the same input, it gives you the same output, and that's pretty much the idea. For space analysis, well, this is going to be n squared. That's fine, because it's going to be dominated by this part. I can be from 0 to n over 2, and mask can be from 0 to 2 to the n minus 1, and this is just, you know, you can think about the bit mask. It has n digits. It has n digits. So every time, you know, so there are 2 to the n possibilities, right? That's just a combinatorial thing. And technically, this is actually much smaller, because note that we always take 2 bits at a time. So for example, you can have odd number of bits used. So this is actually much smaller. But you know, as an upsolving, you could prove the bound on that one. So all possible inputs is equal to n times 2 to the n. And for each n, for each input, we do O of n squared work. So total time is equal to O of n cubed times 2 to the n. And given that n is equal to, and I use n as 14, so I don't use it that way. So yeah, so you could do the math. Roughly speaking, 14 to the cube is 2000, and 2 to the 14 is, yeah. So it's about 45 million, but again, a lot of these 2 to the n is not reachable because of the odd number. So I don't know how, is it just half? No, it's probably less than half, but I don't, yeah, you can do the math at home. But that's roughly the upper bound, and then space is just equal to n times 2 to the n. So yeah, and of course also this is, you know, n over 2 for the I part. So if you want to be tighter in the math, it's going to, you know, that's why it is fast enough, even though this number looks pretty scary actually, or this complexity. Cool. Yeah. And in the beginning, this just sets all the things available to be true. That's basically it. Let me know what you think. You can watch me solve it live next, and I will see you, or you could see the other Larry in a second. Wrong answers. That was a YOLO, to be honest. Oh, only 7? It's really awkward. This is easy. I wish Q2 didn't destroy me, or Q1, I guess. But yikes. Why is this wrong? I can see why Pure got it everything in like 5 minutes, but still. Why am I wrong? This is the story of my day today. Like I should know this. Because everything should be good, but I'm not. 1 times 36. Minus 3 is 12. QCT is... Did I mess this up? Oh, wow, I am dumb. I am dumb. Doo-doo-doo. What a dumb gun. Thanks for watching. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. And yeah, stay good, stay healthy, stay well, and to good mental health. I'll see you later. Bye bye.